Alright, so if you're watching this video, it means only one thing, and that you have completed the Investigate an Infinite series, located on page 58 to 59 of your textbook. You've completed it, you're happy with your answers, and now you're ready to verify that you are correct with what you have. So, the first question says start with a square piece of paper. In the lesson, it was suggested that you use different colored pencils to show your square. And your square's getting halved. Or you could just as easily have used a square piece of paper and some scissors and cut them out that way. Depends on what you're feeling like doing. In this video today, I'm obviously not going to be cutting out paper. I'm going to use the colors. So draw a line dividing it in half, and I can tell you that my lines won't be straight. So if we divide it in half, okay, and for simplicity's sake, we're going to create the terms at the same time. So the first term of our sequence is 1/2. Right, so the next term we find by having the the space that's not shaded. And if I took this orange square, I could actually fit 4 of them. So I have 1 shaded out of 4. And I can continue on. So if I take what's left, and now they become sort of rectangular-ish, not so much a square, but if I take that rectangular shape, I can actually fit how many? 1, 2, 3, 4, 5, 6, 7, 8. So I can fit 1 shaded out of 8 squares. And we do it again. This one's again a little more of a square. And this time, if we're halving this again, we should be noticing by now that if we take this green one, we should have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if we take a, oops, that's kind of a large comma there. I'll just fix that. More like this. And if we look, we notice that 16 is twice as much as 8, 8 is twice as much as 4, and 4 is twice as much as 2. So every time we half our square, or area that's remaining, unshaded, or uncolored in this case, we actually get a smaller fraction, which we can see, but our denominator actually doubles in size. And in order for our denominator to double in size, it means we're multiplying by a fraction, and in this case, which makes perfect sense, you're probably saying it now, is 1/2. Okay, so we can continue on. If we half what's left, then we end up with 1 of 32. And that makes a nice sequence. So then, the next question asks us to predict the next 2 terms for the sequence. Well, that seems very plausible. So we're going to predict the next 2 terms of the sequence. How are we going to do that? Well, we're going to multiply by 1/2. And 1 over 32 multiplied by 1/2 is 1/64. And 1/64 multiplied by 1/2 is 1/128. Okay, so the answer to number 3 is 1 over 64 and 1 over 128. Those are our next ones. Okay? Next question asks us is the sequence arithmetic, geometric, or neither? Justify our answer. Well, we know that we have a common ratio, and the common ratio is 1/2, so it's going to be geometric. And let's just write that down for you. So 4 is geometric because B/C, short form for because, it has a common ratio. Of 1/2. Alright? And then 5 asks us to write the rule for the nth term in the sequence. Well, we know that the nth term in our sequence, so term t sub n, is equivalent to 1/2 to the power of our term number. Okay, so if you're thinking, I'm not really sure where that came from, well, if you think about it, 1/2 for t1 to the power of 1 equals 1/2, right? 1/2 squared, right, is 1/2 times 1/2, which equals 1/4, right? And so on and so on. So that's where the n comes from. We get our n by our term number. All right? Let's go and erase that. All right. Boom. All right, and then question 6 says, ignoring physical limitations, because obviously you can only cut paper so much and you can only shade squares even if you have a very large one, could this sequence continue indefinitely? So in other words, would this be an infinite sequence? Explain your answer. Well, because we can keep going and going and going, it is an infinite sequence. Okay. Our term value will continue to decrease, but it's never going to disappear. So our fraction is just going to have a larger and larger and larger and larger denominator. Okay? So we're never not going to have another term that we can generate by multiplying by 1/2. Okay? So now I'm just going to go to, just going to go to another slide here because it's getting kind of crowded. So, question 7 asks us, what conclusions can you make about the area of the square that would remain unshaded as the number of terms in the sequence approaches infinity? So as we continue on and on and on and on, the remaining area is going to approach 0, right? So the larger and larger and larger our fraction gets, sorry, that might be confusing. The larger and larger our denominator gets in our fraction, then the smaller and smaller our number gets. It's going to continue to approach 0, but alas, it's not going to reach there. So the remaining area will approach 0. Okay? So now the graphing calculators that we've come to know and love so much. So what you should have done is taken your graphing calculator, input the function y equals 1/2 to the power of x. You would have used your table of values from the calculator. What happens to the value of y equals 1/2 to the power of x as x gets larger and larger? So as we increase that exponent, okay, so as x increases, 1/2 to the power of x decreases and approaches 0. So let's just write that down so you can have something to look at. Okay, so this is question 8. So as x increases, decreases. So as you increase your value of your exponent, when you have a fraction, then your value overall decreases, and if it decreases, it approaches 0. So we're getting smaller and smaller. We're never going to reach 0 shaded squares. There's always going to be a square left to cut or draw in half. Okay. And B says, can the value of 1/2 of x ever equal 0? And we just answered that. And no, it can't. Because there's always going to be some unshaded area left to shade. Okay. So question 9, the geometric series, and then that we've been working with, can be written as sorry, I should use a different color. Just to stay with the theme here. Can be written as 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the power of 4 plus so on and so on and so on to 1/2 to the power of x. So you can use the general formula to determine the sum of the series, and it shows you how to do that. Okay. It says enter the function into your calculator and use the table feature to find the sum of s sub x as x gets larger and larger. So what happens to the sum s sub x as x gets larger and larger? So as we increase our value of x, okay, the sum approaches 1. Okay, so as x increases, and that doesn't really look like increases, but it is. Oops. Oops. Okay, there we go. Okay, so as x increases, the sum approaches 1. Right? And if you think about that, we were dealing with one whole square. We're never going to have more than one square, and because we're always looking at chopping that square in half, we're actually never going to actually have one whole square unshaded, because our first term was generated after we cut our square in half. Okay? So B asks us, like the question. So B says, will the sum increase without limit? So will there ever be a limit? And the answer is no. It will never actually reach 1, as we just said, because there will always be a small section of the paper unshaded. Okay? So no. There will always be a section unshaded. Right? And that makes sense. There's always going to be a section shaded, there's always going to be a portion unshaded. Okay? So you can go ahead and pause this if you need to write that down, but you're probably with me, so I'm going to go to the next, maybe, then, oh, I had another slide. Go to the next slide so that we can look at question 10. So question 10 says, as the value of x gets very large, what value can you assume that r to the power of x becomes close to? And the answer to that is, as we know, I know you're saying it with me right now. Okay, that's a pretty color. It's going to approach 0. Okay. And then B says, use your answer from part A to modify the formula for the sum of the geometric series to determine the sum of an infinite geometric series? Well, we know that the sum is S sub n equals our first term times 1 minus our common ratio, the power of n, divided by 1 minus r. And since r to the power of n approaches 0, then 1 minus r to the power of n approaches 1. So we can modify our formula so that S sub n is equivalent to our first term times 1, right? Because we know that it's approaching 1, divided by 1 minus r. And if you went ahead and wrote your formula as S sub n equals t sub 1 divided by 1 minus r, you're still correct. You're still absolutely correct. Right? So remember that because r to the power of n, okay, is approaching 0, that means that when you have 1 minus r to the power of n, which is essentially 1 minus 0, it's going to equal 1. Oops, 1. Okay? So then, final question, last but not least. Use your formula from part B to determine the sum of the infinite geometric series. And we can do that, but we already know the answer. Oops, sorry. The answer is S sub n is equivalent to our first term, which is 1/2, divided by our 1 minus r, and our r is 1/2, which equals 1. Okay? And that is it for this investigation. So hopefully you were on par with what was revealed here in this video.